So first of all, I really just wanted to thank the organizers for accommodating me speaking on Zoom. I'm so sorry that I can't be here right now. So my name is Hana Schiff. Judith, who you just heard from, is my PI. I'm collaborating with Paul McCarty and Alberto Botticelli and Alfonso Guerrero. And I'm a second year PhD student at the University of California, Irvine. Okay, so thank you for introducing me. I'm also going to be talking about spin groups for weak spin orbit coupled materials. Just to give you a brief outline of what I'm going to go through. First, I was going to give a little bit of an introduction on symmetries and weak spin orbit coupling. Although based on the questions that I can hear from the audience and some of the talks that we've heard, it's clear that there's a good knowledge of symmetries already. So I apologize if I'm being redundant. Then I'm going to introduce what the spin point groups are and the different kinds of spin point groups you can have. And then I'm going to talk about their co-representation theory. So my ultimate goal in this project has been to derive the irreducible co-representations of the spin point groups, as there's a massive lack of knowledge of the representation theory of spin groups in the literature. Okay, so as I'm sure you all know, symmetry has a long history of being very useful to us in condensed matter physics. And when it comes to the crystallographic symmetries, usually we start with just the point groups. The point groups typically will describe systems that are finite, but they don't have to, and all of the symmetry elements intersect at a point. And when we're interested in crystallographic systems, the point groups have to satisfy that the rotation axes can only be of orders 1, 2, 3, 4, or 6. When we introduce translations into the mix, we get 3 different kinds of groups: the line, layer, and space groups. There are 13 infinite families of line groups, 80 families of layer groups, and 230 space groups. And I think the space groups are the most well-known. So usually when we talk about these kinds of groups, we're talking about spinless systems. And if we want to start introducing spins into our systems, we often like to start thinking about time reversal symmetry as well. And from a group theoretic perspective, this is exactly what the magnetic or the Shubnikov groups do. They incorporate time reversal symmetry. But they do so by implicitly implying that there is strong spin orbit coupling, because the assumption is that the spins will transform in the same way as the lattice. So usually we will characterize the magnetic groups in 3 different ways. So sort of schematically or visually, if we imagine that up spins are this white color, the down spins are a black color, and sort of like a rapidly fluctuating paramagnetic sort of state is this gray color, time reversal sends white to black and gray to gray. And the 3 kinds of magnetic groups, colorless, gray, and black and white, tell us the extent to which time reversal symmetry is incorporated. So in the colorless case, clearly time reversal symmetry is just simply not a symmetry. Whereas in the gray case, it is. And so in the gray case, we have pure time reversal symmetry. But in the black and white case, actually, time reversal alone isn't a symmetry. However, if you include the composition of time reversal with, for example, like a vertical mirror plane, then this would be a symmetry of our system. And this is usually typical of either something that's kind of antiferromagnetic or similar. So when we start allowing translations as well, we get 50 possible magnetic Bouvet lattices. And in combination with the point groups, we get a total of 1,651 magnetic space groups. This is a lot of options. And typically, when we want to start incorporating symmetries into our physical description, we need our group elements to be operators so that they can act on states and commute with their Hamiltonian. And formally, we achieve this using representation theory, where we assign to each group element an operator in such a way that they satisfy homomorphism. And it turns out that in some very special basis, these matrices will all become block diagonal. And these blocks that appear are called the irreducible representations, and they are a characteristic of the group alone. And this gets sort of complicated when we start dealing with time reversal symmetry. Wigner showed in the 60s that time reversal always has to be represented by an anti-unitary operator. And so we lose linearity, we lose the homomorphism condition, and so we call these co-representations instead. We do still have this building block sort of nature, and we call those building blocks co-irreps. And I'm not going to go into too many of the details, but you can find the co-irreps of groups that have time reversal symmetry by using the irreducible representations of this like halving group G that does not include time reversal symmetry. So this G is a regular group and it has some irreps. And basically you turn a crank called the Dimick indicator, and you can classify those irreps into 3 types. And based on the type, there's just a very simple algorithm summarized by the table here that tells you how to construct the co-irreps of your non-unitary group that has time reversal symmetry in it. So with regards to spin orbit coupling and how this relates to topology, we've been very fortunate to hear a lot about topology, and I won't have time to talk incredibly much about it here, but there are some uncharted territories. For the most part, well-studied systems are those that are either non-magnetic, both with and without spin orbit coupling, or magnetic materials with strong spin orbit coupling. But in terms of doing an adequate symmetry analysis, non-magnetic materials have symmetry groups that are ordinary groups, and these strongly spin orbit coupled magnetic materials have symmetry groups corresponding to the magnetic groups. Whereas there's this largely unexplored region of magnetic materials with weak spin orbit coupling. And actually, in order to use symmetries to analyze these materials, we need what are called spin groups, which go beyond the magnetic groups and the ordinary groups. And actually, the spin groups as a whole contain within them the magnetic and ordinary groups, but there are also many other groups that have not yet been used. So most of my goal has been to examine these groups and their representation theory. They were introduced in the 70s by Litvin Opatowski. In 1975, Litvin himself, he enumerated all 598 non-trivial spin point groups. And then there is a gap of about 50 years until any more work has been done. And even since the, around 2012, very few people have been actually looking at these groups in a systematic fashion. So one thing that's missing is the irreducible representations of the spin point groups, which are going to be crucial for our understanding of systems and many of their properties, topological or not. Also, the classification and enumeration of the spin space groups and their irreps are missing, as well as, of course, the topological classification that follows. So my research so far has been on actually just finding the irreducible co-representation of the spin point groups. So it seems like these will be applicable to quite a great deal of systems. So already, when we're looking at magnon topology, it has been shown that the Kitaev hyper honeycomb lattice, it has some additional degeneracies that can't be explained without the spin groups. And these degeneracies are crucial to understanding the topology. In the past decade, there's been a very influential technique called topological quantum chemistry, or symmetry indicators, that is a systematic classification of symmetry protected topologies. And this requires knowledge of all of the space groups and co-irreps. So this is one avenue that we think could be very promising. There are specific materials in the literature that people have indicated have this weak spin orbit coupling regime where the spin groups are going to be necessary. And maybe slightly controversially, the spintronics community seems to be very excited about ultramagnets. And I don't know that much about them, but what I do know is that you cannot understand the symmetries of ultramagnets without using spin groups. So there's a lot of avenues in which the spin group should be useful, and having their representation theory is going to be crucial. And so far, it does not exist in the literature. So without further ado, what are the spin groups? They describe weak spin orbit coupling. So we imagine the spins being somewhat decoupled from the lattice. So the spins do not have to transform in the same way as the atoms in our lattice or our molecule do. I like to think about it as having like a layer where your atoms live and a layer where your spins live. And you can have something happen, some group element acting on the atom. That would be this purple part. And we usually symbolize the spatial part as in the right side of a pair of two elements. And in the spin space, that's this pink part, we can have a completely different group element acting there. And you can see here in the bottom left, hopefully, how one of these elements, B double bar R, acts on a magnetic moment. And all of the space groups can be expressed as a direct product of this little b that acts only on the spins, and this capital S, which is called the non-trivial group, and it has no elements that act only on the spins. So there are 4 different kinds of spin point groups. The non-trivial ones, which I just introduced, they actually correspond to spatial or like non-coplanar, non-collinear arrangements of spins, and there are 598 of these. And then there are three other kinds, the non-magnetic kinds, where we can characterize them by having a spin-only group that has time reversal symmetry, coplanar spin point groups, where the spin-only group contains a mirror plane in the plane of the spins, and then collinear spin point groups, which have sort of like C infinity V spin-only group, where you have an SO2 around the axis of the spins and vertical mirror planes that contain the axis of the spins. So basically, with the way that we have broken down what the spin point groups are, this is how we'll go about trying to figure out what the co-representation theory is in each of these four cases. Right, so there's 972 just point groups in total. So it will probably be a lot of space groups. Okay, so for the non-trivial spin point groups, which remember those correspond to like spatially oriented spins, it turns out that there's a very special isomorphism between these groups and black and white or regular point groups. So I'm not going to go into the group theoretic details here, but essentially if S includes time reversal symmetry, it's going to have the same irreducible representations as G, where G is the normal point group that you would assign to the symmetries of the molecule or the lattice. And if S is not unitary, or in other words, it includes time reversal symmetry, you can show that it will have the exact same co-irreps as a black and white point group that comes from the same family G. So just, I'm not going to go through the math here, but as a sort of example of how you could verify this, on the left, I have a molecule with black and white point group symmetry, and on the right, I have a molecule with spin point group symmetry. And in both cases, the sort of unitary halving group is C2V, so they share the same halving group. And so therefore, we're going to be, when we do that induction algorithm, we'll be starting with the same table of C2V irreps. And when we turn the crank on these irreps, we will find that we get the same type in both the black and white and in the spin point group case. And because these are sort of the only two ingredients of our algorithm for deriving co-irreps, this will mean that the spin point group has the exact same co-irreps as the black and white point group. So we went through and actually verified this manually, but we were also able to prove this from a group theoretic perspective. So in the other three cases, just for the sake of time, I'm sort of going to flash through two of the results and then maybe explain a little bit more a third one. In the non-magnetic and coplanar cases, one can show, and in part using the isomorphism theorem from the last section, that the total spin point groups are going to have the same co-irreps as a gray point group, where the gray point group is built from that spatial parent point group that describes the symmetry of your molecule, and that's G. So in both of these cases, the co-irreps look like G plus time reversal G. So this is not incredibly exciting because these co-irreps already exist. But it turns out that in the collinear case, we will have new co-irreps. And sort of the reason for the new co-irreps, especially in the case where this group has, where the non-trivial part has time reversal symmetry in it, the reason is because if you remember in our recipe for coming up with new co-irreps, we have to start with irreps of that unitary halving group. And it turns out that we don't already know these irreps ahead of time. So that's sort of what is boxed here in yellow. This group is sort of complicated. It's not just a direct product group. So we can't just take the direct product of like SO2 and S star. Instead, we have to find these irreps first. And there's another algorithm that's very similar for finding these. And so first one has to find these irreps, and only then using the recipe from the beginning of the presentation can we start looking for the new co-irreps. And so this is exactly what we did. And as a result, once we finished this part, we had found all of the co-irreps and irreducible representations for the spin point groups. So sort of just to summarize, because this was rather quick, I wanted to save time for some questions. The first two things that we did was confirm what already exists in the literature, was just confirming that the enumeration of non-trivial and total spin point groups is correct. We did get the same result. And then we found that the non-trivial spin point groups have either the same IREPs as their spatial parent group or as a black and white point group formed from that spatial parent group. We found that the non-magnetic and coplanar spin point groups have the same co-IREPs as the gray group formed from the spatial part V. And we found that in the case of collinear spins, the collinear spin point groups have new co-IREPs. And all of these have been tabulated, and hopefully a manuscript will be submitted relatively soon. So thank you guys so much for listening. I wanted to open up the floor for questions because this was kind of fast. And thank you so much.
All right, let's thank Hana. Questions? Hana, I actually have a question, and maybe I mean, this is really impressive. Just say that, but going back to maybe starting point of weak spin orbit coupling. At the end of the day, right? Even if it's weak spin orbit coupling, the spin will have to point along one of the directions that that are enforced by the crystallographic symmetries, right? Like I can. If I think of materials like iron-based superconductors that are not have large spin orbit coupling, in the end, moments pointing along the bonds or perpendicular. So how do I think of this in terms of if I think in terms of a phase transition, I can say, oh, this perturbation, weak spin orbit coupling is always relevant, but maybe small, so away from critical point, I don't need to worry too much about it. But in terms of symmetries and classifications, how do I think of this crossover or this going from a spin group to a magnetic space group?
Okay, if I'm understanding your question correctly, you're asking if I'm thinking about two phases and I'm trying to go in a phase transition between them. And one phase, let's say I start off in a description where it's a spin group and then I move to like a magnetic group. So like, I don't know what exactly physical manifestation of this would be. You're asking, how do I know which magnetic group I will get from a spin group?
No. Well,
or what exactly?
Well, my point is, the spin will have to point along one of the directions that are enforced by the lattice, because even if the spin orbit coupling is weak, right? You can't avoid it. You never have true SU2 invariance, right? So, yeah, that's an energy scale. I agree. Sorry, there was a comment here saying it's a matter of energy scales, which I completely agree. My question is, how do we incorporate that into a symmetry classification?
So you're saying like, how do I draw the line between like what is weak and strong, and how do I know which groups I should be using?
Yeah. So if I start, let me reframe. I think Eduardo said something that how do I go from a spin group to a magnetic space group? How do I describe that?
Okay, I can say a couple of things here. So in terms of deciding whether or not you have a weak spin orbit coupling or a strong spin orbit coupling, that's sort of, obviously that's a gray line. And actually I sort of propose thinking about it in almost a reverse fashion. I would say that you know that you must have some decoupling of your spin and lattice degrees of freedom if you need a spin group in order to describe the physics of your system. So that's sort of like comment number one. Comment number two on how to go from a spin group to like a magnetic group. This usually is not difficult because like I showed here on this picture, the magnetic groups, they're contained in the spin groups. So from a symmetry perspective, if that transition is happening, the magnetic group that you will end up in must have been a subgroup of the spin group that you started it with.
Yeah. So, okay. Yeah. Sorry. You're saying something more. Sorry.
No, that was it. I think that was what I wanted to say.
Yeah. No, I agree.
The question right.
Yeah. No, it's exactly that. I guess the question would be: is it easy? I mean, maybe with the tools that were developed to find these subgroup relationships. Which magnetic groups are subgroups of a given spin group. Maybe it's already been done. Again, I don't know. I'm not, and I'm just curious. But I have the impression.
Yeah, nobody has done that mapping yet. But that should not be incredibly difficult to do because basically what you're looking for is, if I can go back to, let me go to this slide here. Basically, what's characteristic of the magnetic groups is that you have the same like if you're looking at the proper part of the spin element, this B here, I don't know if you can see my cursor.
Yes, yes.
But the proper part of the B, if it's the same as what's happening in the R, then that's what the elements of a black and white group look like, because what that means is that you did the same thing to the spins as you did to the lattice. So like if I had R was equal to C4, then B could be either C4 or time reversal times C4. That would be characteristic of an element that must belong to, you know, if those are the only kinds of elements you have, then that's a black and white group, because you have done the same thing on the spins as on the lattice. So I think it would really just be about going through and just finding which groups have those properties. Not many of them do. I will say that what Litvin did originally, so in the 1975 work, that was his PhD thesis, he wrote down a list of all of the non-trivial spin point groups. He did write down which ones correspond exactly to a black and white group, but he did not write down which spin groups contain a black and white group as a subgroup. So that would be really interesting to do, to sort of map out what the possible transitions could be. Yeah.
Okay. Any other questions? I'm sorry that I asked like 5 questions, but
no, I'm sorry it took me so long to figure out what you were asking.
We have one more question.
So if you somehow are dealing with magnetic ordering, which is incommensurate with the underlying lattice, and do you have to consider an even bigger set of groups?
Okay, so at this point, we're still talking only about point groups, so I have not included translations yet in here. But it should not be the case that you have any additional point groups that you need to consider if you have an incommensurate system.
Yeah, I think usually in that case, you have to go to something called supergroups, because you don't have translation variance. Anyway, I think, any more questions? Hannah, thank you very much for a very interesting talk.
Thank you guys so much.
And we will be back at 11:10, okay? 11:10.